around here. We were just talking about Lizzie, right? Um, we said Lizzie could jump on the trampoline, then she'd go up, then she'd fall, she'd start screaming, right? So we were converting one form of energy into a very different type of energy, like a sound wave, right? Did I tie that to the Spectra or the photoelectric effect yet? All right, started to. So let's just go ahead and start right now then. So when it says Einstein used this assumption, his assumption was what Planck's assumption was, or Planck is the correct way to say it, but I don't care. And that was that energy was quantized, meaning that it had certain values, and if you didn't reach certain values, nothing would happen. So if you remember, the photoelectric effect said that certain light would come in and nothing would happen, but if you change the wavelength of the light or the color, something does happen. And wavelength corresponds to energy. So Einstein says Planck must be right. Energy must be quantized, and the photoelectric effect proved it, because only certain colors of light would cause something to jump up. Just like if my daughter Carly, who's 4 years old and weighs maybe, I don't know, 40 pounds, I really have no idea what she weighs, but if she is playing crack the egg with Lizzie, is she going to even bounce her off the trampoline? Probably not. Maybe my 7-year-old, maybe, but definitely not going to get her up very high, right? Switch to my 13-year-old. Now she's probably bouncing but not going anywhere. You have to have a certain high enough bounce before any action happens and crack the egg. We all know that, right? Energy is the same way. The photoelectric effect is the same way. The energy has to be, threshold has to be met before anything actually will happen. All right? This photoelectric effect experiment is fairly famous for proving that light has wave-like properties, but like Planck says, it also has particle-like properties. And that energy itself is what we call a quantized value instead of a continuous value. The slide we usually use for that, or a thing to describe that, is that picture you were supposed to draw. This is working fantastic. And, whoops. It was this idea that energy is more like going upstairs than walking up a ramp. Energy only has certain levels. It doesn't have infinite levels or values. All right? The distance between is proportional to the energy. And the idea is that one step here would be one quanta, which has a numerical value equal to Planck's constant, which is on a slide coming up. I don't know. It's tricky, but it's not the hardest thing to understand, because our monetary system is quantized, as we've talked about before. And what's the smallest number that we can have? A penny. Everything that we have money-wise is based on a penny as the smallest, and everything's a multiple of that. You okay with that? So the penny and the quanta are similar. They're the smallest value of their thing that we are talking about. All right. Now, it's going to get trickier. So therefore, if one knows the wavelength of light, one can calculate the energy in one photon or packet of that light. And I think we rewrote this equation. We should have it in our notes already. Is that correct? Okay. All I did is I took C equals lambda V, and I substituted V into the E equation, and we combined to get the energy of a color or a photon, whatever we want to talk about, is equal to hc over lambda. All right, this value for h is, I went past it then, right there at the bottom. I think I was saying it right. I might have said 6.4. That's a value that you have to be able to use from now on. All right. So if you would, please take out your little half sheet that you colored the things on. Oh boy. Hi, family or wife. All right, and then please find your value that you, or your drawing that you had for hydrogen. Hydrogen. Seven was, or it was the one over here that you were supposed to do. If you didn't do it. Okay. All right, well, if you don't have hydrogen, just look up here. Hopefully some people do have hydrogen. Hydrogen had a bluish purple line around somewhere. Can someone tell me where that was? About right here. Okay, what were the other lines it had? Had red way the heck over here. Around here. What else did it have? Right around here. 5. Okay, then a lot of times you won't see one, but there is a purple one. Is that purple? We'll go with that. There's a purple one about right here that's super faint. All right. What we're going to do now on the back of your paper, and this will help you because this is, I thought we'd get there Friday, but this is the multiple or free response. What I want you to do is calculate the energy of each color. So let's make a standard here. So let's say purple was around 410, blue was around 450, we'll say green was about 500, and then 680. Now, these values here are all in nanometers. So we have an equation to find energy from wavelength. We just barely wrote it down. The equation was E equals what? HC over lambda. Now, what is C? Good. Make sure you use the nanometer value. H is called Planck's constant. And that was that 6.63 times 10 to the negative 34. And then the wavelength, that's the numbers we just looked at. Okay, it's good practice. Find the energy for each of the 4 of them. This is hard with a standard calculator because you have crazy big exponents. But if you know your math rules for exponents, you can get it done. Okay, take a few minutes. All right, so if you did not get it right, I'll do at least one. So my E is equal to HC 6.63 times 10 to the negative 34. That's HC is in nanometers, right? 3 times 10 to the 17th nanometers. This all works out, so you don't need to really write the units out. And then, I don't know, what was one of them? 410 was the first one, right? So you would type that in. If you if you want, the top unit is just going to be negative 17, right? And you're going to divide it by 100, basically. So right there, you should know your exponent's going to be negative 19. Anyway, type that in, and you end up getting 4.85 times 10 to the negative 19. Not very hard, right? Okay. This answer, make sure you know what this answer, what it is. It's the energy of one photon of, let's see, I did 410, so that'd be the purple, right? Now, the test question will follow this up. It'll give you the information. It'll say, what is the energy of one photon of light? Then it will say, what is the energy of 1 mole of those photons? Okay. And that might seem difficult, but it is super not difficult. How do we convert something to a mole of something? Multiply it by the big number that everyone's forgotten. The Avogadro's number, so you would take this number and multiply it by 6.23 times 10 to 6.02, sorry. There's a 23 coming up. Times 10 to the 23rd. What's that? This is called Avogadro's number. That's how many things there are in 1 mole. So you just multiply your answer by Avogadro's number. Avocado and his guacamole. All right, you okay with that? We're going to do one now to make sure it's locked in. So this question is exactly like the one on the test, except for this number is different. Okay? So I'm telling you right now, this is the question on the test. There's one more sliver, which we'll add at the bottom. Well, actually, I think there's 2 more questions after this. They're not math, they're conceptual. So take a few minutes and see if you can solve that problem. I'll work it through, but let's go ahead and I'll just show you the answers. All right. So these were the 3 equations that were given. C equals lambda rho, or frequency. E equals hv, or frequency, or rho, whatever you want to call it. And E equals hc over lambda. You can use, well, you have to use this one. Well, really, you can use whatever you want. So we end up with our frequency being 5.4 times 10 to the 14, or is that a 19? 14, okay. Seconds on the bottom were S negative 1 hertz. Who had that answer right? Nobody did? So what did I do wrong? Okay, well, let's come back to that. I'll bet most of you got your energy right, I hope. How about the energy of a single photon was 3.58 times 10 to the negative 19? Who had that? Raise your hands. Okay, now we're doing better. Okay, then the energy of a mole of these would be 215,743, or 2.16 times 10 to the 5th joules per mole. Who had that answer? Raise your hand. No, new man? Oh, sorry, wow, it was perfectly hidden. All right, so I guess let's go look at frequency. What did you guys have? Do you all have the same different number than I have? What do you have, Newman? You didn't do it? Nope, nanometers is wavelength. Okay. Well, better remind you, we do have an equation to find frequency. There's two versions of it. You can use either one. It's the speed of light is equal to wavelength times frequency. This is a constant, so you could plug that in. So you would end up with it being the speed of light divided by wavelength, which is what this is. That's how I did it. All right. Or you can certainly find it here also. Energy is equal to Planck's constant times frequency. So you take the energy and divide it by Planck's constant. Either way, you should get the same value. You'll probably be off a teeny bit just because of you're using the 6.63 here. Here you're using just 555. But they should be close. Are you okay with frequency? You sure? Okay. All right, here was my attempt at some Spanish last year. Oh, and German. Yeah, we're a trilingual class. This is saying warning or caution. I don't know, warning, I think. Attention, thank you. I don't know. This pregunta es en la examen. This is on your test, but there's two other parts. Are you ready? Here we go. The next part of this question would say, would you expect this to have come from a large or a small fall? Okay, so let's talk that through. Remember this thing? It was 4, 5, 6, and 7, right? Whoa. That just blew my mind.
I thought it was 8 next.
So what was this number that it gave you? 555. I guess this would be a bad example to use on this one. On the test, it's either here or there. Okay, so it's a little easier. So you would say this came from a medium fall, probably. Now, what I mean by that is, when does an electron give off light? When it's popped up high, but then it falls back down, right? Large fall, it gives off large energy. Small fall, it gives off not large. All right, now this is tricky. Over here at 700, that's actually red. And down here, just pretend this is purple. This is purple. Because the smaller the wavelength, the higher the energy. Is everyone okay with that? So on your test, if I give you a number and it's on here and it's way over here, you would say this came from a large fall. Because it is short wavelength, high energy light. If it's over here, you would say it came from a small fall. And we'll get more into the fall and that here in the next few slides. But just remember, light is emitted from the atom when an electron absorbs energy, is promoted to a higher level, but then falls back down. The distance it falls is directly proportional to the energy that it radiates out. Okay, you all right with that? And then the last part, I can't remember how it's worded, but it said, what color would you expect this light to be? So you need to sort of have Roy G. Biv memorized, okay? So it's really backwards, but so we got red, orange, yellow, green, blue, indigo, and violet. Vibiroar. Vivior. Bivgior. All right. So you do need to have this memorized because that should be an easy 5-point question right there. That's easier than finding a limiting reactant, right? Like, oh, hey, it's at 550, it's right in the middle, it's probably around green. Or it's 420, it's around violet or indigo. I would accept, well, really, I'd accept any violet, indigo, or blue. And on the low side, I'd take yellow, orange, or red, probably. Depends on how caffeinated I was. Now, that's half of the next test. That problem is half of the free response. Yeah, this is not, I don't know. And I don't even know what the second one's going to be yet, because usually the second one's from Chapter 7, which we're not going to do until next try. Yay. So we'll start Chapter 7. I just won't test on it. This class, AP is actually Latin for no fun. I want to take days off and just relax and watch movies in Spanish, subtitles, but I just can't do it. I didn't make fun of Spanish teachers, did I? I mean, like periodic table symbol subtitles. That would teach me a lot. All right, are we ready for the next slides? Make sure that you indicate to yourself that that's on your test. There's no reason not to do perfect on it. Did you find your sister down there? Oh, sweet. You know what I hate more than, I gotta turn my video off here. Moving on. So these two problems, you probably don't have your books with you still, but these two problems are just like what we just did, and will hammer into your brain that these aren't that hard. All right, next. Okay, so the rest of the hour we're going to talk about this weirdness. It's called the nature of energy. It's already been bizarre. But another mystery involved the emission spectra observed from energy emitted by atoms and molecules. So this is what you looked at. It's different than the photoelectric effect, but it's certainly the same exact idea. Okay, so this is neon that's being electrified and it glows orange. We had hydrogen, we had neon, we had krypton, and we lit all these things, and you notice they all gave off a different light signature. All right? When you look at these, they do not give off a continuous spectrum as one gets from a white light source. Only a line spectrum of discrete wavelengths is observed. All right? So these things that we drew, they are called the line spectra. It's the colors that are produced. It's kind of hard to see with that light on, but like super hard to see. There are things. Oh, that's not what I wanted to do. Wow. There's 4 lines, I promise.
4? I see 3. Oh, wait,
One, 2, 3, 4.
Wait, what? Those are really. Oh, I see. I see the red. I see the red. I didn't even see that.
Look at that.
Oh, hey, look, there's actually stuff there. Oh.
All right. So when we look at these, their explanation of light didn't quite make sense. The idea of quantization will make sense, and Niels Bohr is going to come along and explain it. And this will help explain what I was talking about when I was talking about electrons falling. It says Niels Bohr adopted Planck's assumption and explained these phenomena in this way, and it was pretty genius. And he said that electrons in an atom can only occupy certain orbits corresponding to certain energies. So Bohr's model is typically called the solar system model, like our planet. Our planet would be like an electron, and the sun would be like the nucleus. Our planet lives on a specific orbit around the sun, right? Bohr's saying these electrons live on these lines. All right? Another idea of his. He said electrons in permitted orbitals have specific or allowed energies, and these energies will not be radiated from the atom, meaning that the electron does not lose energy. All right? So they're going to live here, they're going to buzz around, and they're never going to lose their energy. All right? Next, energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another. The energy is defined by E equals hv, or E equals h times the frequency, which is what we've been using. But remember, we substituted the equation for frequency in, which was c over lambda, and just combined them. All right? So what he's going to say now is you can move an electron up and down, but it has to be a multiple of Planck's constant, which should make sense, sort of, because remember, every form of energy is a multiple of Planck's constant, just like every value we have is a multiple of a penny. Right. Yep. All right. Now, he put the math behind here that it works out really well. The math is this. So, the energy absorbed or emitted from the process of electron promotion or demotion can be calculated by the equation. The change in energy is equal to negative RH over 1 over NF2 minus 1 over NI2. Write that down. You have to use this. No. Or sorry, yes, they are squared. I said 2, but yes, those are both squared. It's not as ugly as it looks. Yeah, it's final and initial. It's talking about the ring it starts on and it ends on. This calculator's pretty old. The only way to turn it on is to hit it. All right. So what this is saying is we can literally calculate if I had an electron here on this ring and it fell back down to the first ring, I could calculate that energy that would be released. I would take this constant and final, we would say it is 1. So it'll be 1 over 1 squared. That's not too hard, right? And then 1, 2, 3, and 1 over 3 squared, which would be 9, right? So I'd have RH times 1 minus 1/9. It's not as bad as you think it is. It'd be that number times 8/9, and you'd have your answer. You okay with that? We're going to do one. Ready? So that's our equation. I don't know, these are from your book, but we'll just say that an electron went from 6 down to 2. What's the change in energy? Times 10 to the what? Okay, here we go. This is kind of cool. What I would like you to do now is find the wavelength of light that came from this drop. So remember, E was equal to hc over lambda, right? That means lambda is equal to hc over E, correct? Constant, constant, the answer I just found. And you'll get a negative value, but we just ignore it. We don't get a negative wavelength, I promise. Yeah, I get around 410 nanometers. Well, I said you'll get a negative number, but we don't have a negative wavelength. This equation, the sign only tells me it's emitted, okay? This equation doesn't matter whether it's emitted or not. Just put in the absolute value of the energy. Does that make sense? Or, just remember, we can't have a negative distance of a wavelength. Okay. It's pretty amazing that we can just talk about this thing going from one place to another, and now we have the color purple. It's pretty sweet. Okay, good job. I would highly recommend doing the first parts of Chapter 6 homework while it's fresh. Or you can wait till Thursday night at 11:45.